out of the Tidewater AREC. My primary responsibility is cotton production. My official title is field crop agronomist for Virginia. But I'm here to talk a little bit about what my lab really works on is enhanced efficiency fertilizers. So I know we have a lot of retailers and a lot of industry folks. So who in here sells an enhanced efficiency fertilizer? All right, who recommends enhanced efficiency fertilizer to growers? All right, just throw out some names of some products. I'm not here to promote any products that you see on the market. Anybody? ESN, I know we got a lot of CPS folks here at this meeting. So ESN is probably the big slow release or controlled release. They market it as a controlled release product. We'll talk a little bit about that. I'll show a little bit of data from some of my research with ESN on corn in Virginia and what we're looking at, as well as some experimental products, slow release, controlled release products that are coming on the market. So you probably heard a lot of soil fertility nutrient management talks. I always start my presentation, so this is what the general public sees when they think of agriculture. And they see a nice ear of corn and they think about their food supply. When I talk to most growers, this is what they're typically seeing when I talk to growers. That's how they view their crop in the field. They're looking to get the biggest bang for their buck and increase their efficiency across the board of their cropping systems. And typically, we'll talk about non-legume cropping systems, so corn, wheat, cotton, any other rapeseed, canola, non-legumes. Nitrogen typically is our most limited nutrient, especially in the coastal plain regions on the Delmarva, but even down into Tidewater, Virginia, where I'm at, and east of 95, really up and down the East Coast, is what we would refer to as the coastal plain. Because nitrogen leaches, it's mobile, but it also is prone to loss other ways to the environment. Ammonia volatilization, we'll talk a lot about ammonia volatilization, some of the enhanced efficiency fertilizers used for that. How many people in here, or their growers or their clientele, are no-till or minimum till systems in terms of corn? So quite a few, and that's been the trend in the Mid-Atlantic, especially in Virginia, switching to no-till. We're predominantly strip-till in the Tidewater where I'm at due to some fragipan and hardpan issues. So when we talk about enhanced efficiency fertilizers, we really have to paint a picture of where we've been and where we're going. This is just a chart of and this is a little antiquated, but this is human population graphed with fossil fuels, the consumption of fossil fuels, but then also the generation of reactive nitrogen. And reactive nitrogen is just those species of nitrogen that are reactive in the environment. So a lot of that comes from our inorganic fertilizer sources or synthetic inorganic fertilizer sources. Has anybody, this green line right here, has anybody heard of Haber-Bosch? We have some industry people, so we should, hopefully everybody in here is familiar with the Haber-Bosch process. That's the process where we take atmospheric in, react it with hydrogen gas under intense pressure, and we make ammonia, and anhydrous ammonia. And then from anhydrous ammonia, we react it with CO2 to make urea, which is our dominant end source that we use in the eastern part of the U.S. Not a lot of anhydrous goes out in the mid-Atlantic, southeast U.S. Most of the predominant end source is urea or UAN solution. So Haber-Bosch is responsible, this process, this industrial process, is responsible for the production of our synthetic inorganic fertilizers. And you can see there's definitely a correlation with human population growth and this Haber-Bosch process. It's speculated that 40% of the dietary human protein worldwide can be linked back to that one process. Without that, that means 2 out of 5 people wouldn't have enough dietary protein in their diet to survive. So that's a very important process, and that's why we're going to be talking about enhanced efficiency fertilizers. So here's the common sources of fertilizer used worldwide. Anhydrous. Granule urea is taken over as the dominant source. It's probably about 60% worldwide, and that's what we're going to be talking about a lot of today is granule urea, UAN solutions, nitrate solutions. Ammonium sulfate is another big player, and that's become more and more important as we need sulfur in our systems where sulfur can leach because we haven't had the atmospheric deposition from some of our coal burning power plants and industrial processes where we're scrubbing that sulfur out of these emissions. Ammonium nitrate's being phased out. You can still get it in some specialty crop areas. And then organic sources, folks in this region know a lot about poultry litter, dairy slurry manure, biosolids. It seems like around the Chesapeake Bay area, Delmarva, we've been dealing with organic sources and how to manage those sources more efficiently. And some of these stabilized products can be used on organic sources to limit some loss mechanisms as well. But when we look at the nitrogen cycle, out of all the nitrogen we apply in cropping systems, the plant only utilizes worldwide about 33%. So if you apply 100 pounds, uptake is about 33 pounds, is what typically we average in cropping systems. U.S., we might be 40 to 50%, but we're pretty inefficient when it comes to managing nitrogen and plant uptake in our ecosystems. These blue boxes are all inputs into systems. Red boxes are all losses from the soil or to the atmosphere. Here we have the industrial fixation, your commercial fertilizers. These green boxes, these green ovals down here are the transformation processes in soils. We have organic nitrogen. If it's mineralized, it goes to the ammonium form, and nitrification then converts that to nitrate. And we'll talk a little bit more about these processes and get a little bit of a chemistry class. I know everybody's excited about that, but in order to understand why we use enhanced efficiency fertilizers, you need to know these chemical processes that go on in soils, especially if you're recommending these to growers, because understanding the transformations in the soil is going to allow you to explain to a grower why this product works and why it's effective under the right environmental conditions. So here we have, this is for granular urea. This is an incubation study we did in my lab last year. Basically, we added just untreated urea at a certain concentration, and we tracked the disappearance of urea and then the appearance of ammonium, which is the green line, with the production of nitrate. So this is just basically shows you what happens biochemically in the soil. When we put urea, the black line, we see that there's no urea left within 3 days in our typical coastal plain soils of actually applying urea into an agri-ecosystem. Ammonium production spikes and then starts to decrease as the bacteria responsible for nitrification start to take over, and then we see nitrification, nitrate becomes a dominant species in the environment. So what does all this mean? Well, these loss pathways are a big factor. So we have ammonia volatilization, which that's urea being converted to ammonium and then it's converted to ammonia gas and we lose it to the atmosphere. It contributes to the formation of particulate organic matter. Has anybody ever been to LA or had the fortunate enough to go to China or Beijing and seen the air pollution and the smog? That's particulate matter in the atmosphere is what you see there. We were in Beijing 2 years ago now, or a year and a half ago, and we couldn't see the sun the day we left. Our flight was actually going to be delayed because the air quality was so poor in Beijing. Nitrate leaching, groundwater pollution, denitrification, production of greenhouse gases, NOx gases, runoff and erosion. With nitrogen, we're typically not worried too much about runoff and erosion in our systems because that's not the major pathways. And then also we have crop harvest, the crop removal in our system. So we're going to talk a little bit about ammonia volatilization because a lot of people overlook this, and in our sandy soils we think a lot about nitrate leaching in our soils and that being the predominant loss way. But typically we can see anywhere from 10 to 50% of our nitrogen from urea being lost in our systems. Typical loss of about 35% in. If we look at the 2016 U.S. corn yield of 175 bushels, we need a pound of nitrogen per bushel of corn. That's equal to average nitrogen rate of 175 pounds. If we have a loss of 35% of our nitrogen we apply, of that 175 pounds, we lose 61 pounds of N to the acre. At 35% nitrogen, that's $21 an acre that we lost just by ammonia volatilization alone in our no-till systems. If we multiply that by 86 million acres of corn in the U.S., That's an annual loss to our economy just through ammonia volatilization of about $2 billion. And that's just loss of nitrogen from our soil. That's nitrogen that the crop never has a chance to take up. This is some ammonia loss from different fertilizer sources. You see urea is the greatest. This is DAP. And then you have calcium ammonium nitrate and ammonium sulfate down here are fairly low. But it just shows you that all nitrogen sources are not equal in terms of their loss potential for ammonia. And this is the reason why. So if you have urea, UAN solution or granular urea, broadcast soil surface, this urea, which is this compound right here, reacts with water to dissolve. There's an enzyme in the soil called urease, and it's ubiquitous. You'll find it everywhere. It's actually in your intestines right now. It's one of the reasons why folks get kidney stones, is because it's converting uricic acid into bicarbonate. And then that reacts with calcium in your intestines to form calcium carbonate in your kidneys to form calcium carbonate kidney stones. So this enzyme is fairly ubiquitous in the environment. It converts urea to ammonium and bicarbonate. This goes back to some high school chemistry, but that bicarbonate decomposes into CO2 and hydroxyl. That hydroxyl raises the pH, which then strips a hydrogen atom off of that ammonium ion. And I know this is a lot of chemistry, but that converts it to NH3, which is ammonia gas. And that's what's lost. We can measure pH changes in the zone of that granule dissolution area as high as a pH 9, even if you have a pH 5/8 soil. That's how fast and that's how effective this enzyme is converting, is that hydroxide will build up in that area to a pH, to get that soil to a pH of 9. And this is a little example of this. So this is 2 days. This is where the urea granule is in the back left corner, and we're looking at, this is soil pH. We're looking at pH. The soil started out at 5.2. 2 days after we applied that urea, we're measuring pHs above 7. Then 4 days out, that soil buffering capacity starts to take over, and we're still above 6.5. So as you see, as you move away to the front of this chart and to the left of this chart of where that granule was placed, you see that pH change is not as great. But where that granule dissolved, that pH change is very prevalent and gets into that basic or alkaline range, converting ammonium to ammonia gas, which is lost in the environment. This is just looking at ammonia volatilization or ammonia production with temperature and its pH. So as pH increases and as temperature increases, you see ammonia production increases as well if you have straight ammonium. And this is important because that urea hydrolysis reaction, it controls all of this in the soil. And so if you have warm temperatures and soil that doesn't have a high buffering capacity or low CEC, which is typical of our coastal plain sandy soils, you get a great pH change and you have a greater potential for ammonia volatilization. So nitrification. So now, say we're going to protect against ammonia volatilization and we were looking at nitrification. So what do we want to look at? So this is the process of ammonium to nitrate. And it's actually a bacterial-mediated process. There's two species of bacteria. You got Nitrosomonas and Nitrobacter. Nitrosomonas converts ammonium to nitrite, and then Nitrobacter converts nitrite to nitrate. This is the rate-limiting step here. Nitrosomonas is fairly efficient, but Nitrobacter is much more efficient. And that's because the soil system has evolved. Nitrite is very toxic to plants. So if it builds up, we have a problem, and it's going to become toxic to plant roots, and it's going to really have an impact on our plant growth. So this species converts it to nitrate, which plants take up readily. This is this chart showing as soil moisture increases, nitrification increases. These are biological reactions. You need water and you need warm temperatures to mediate the speed of the reaction. And then this is just showing a relationship of nitrification and temperature. Like I said, the warmer the temperature, the faster the reaction. This is why in the Midwest they can go in the fall with Anhydrous, knife it in, and come back in the spring and it still be there as ammonium and held on exchange complex because the bacteria, the soil microbes are not active in really, really cold soils. So this is why they have that practice in the Midwest, and it's pretty effective. So now we're getting into the meat of the talk, the enhanced efficiency fertilizers. And one thing we're going to, Steve kind of talked about in last, is the 4 R's of nutrient management: right source, right rate, right timing, and right placement. And really enhanced efficiency fertilizers touch on each of those. So they really depend, which ones you use depend on the source of nitrogen you're using. Rate is going to be dictated by crop yield, like Steve said. You don't want to leave anything on the table. Timing, with some of these slow controlled release, when you apply that nitrogen, that enhanced efficiency fertilizer is going to be critical. If you apply something like a polymer coated urea too late, you may limit yields because that nitrogen is not available for increased plant uptake. So understanding what timing you need to put these enhanced efficiency fertilizers out is critical. And then right placement. So how many folks have clientele that, a fair amount of the clientele that are injecting UAN solutions? That are injecting. Would you think you need an ammonia volatilization control, like something like an NBPT product, Agritane, Lemus, there's some other products on the market, when you inject UAN? Not as much. Yeah, depending on how deep you're putting that UAN, if you're putting it 3 to 4 inches in the soil, you're probably not going to need to spend money on Agritane or an NBPT containing product for ammonia volatilization control. But if you're dribbling that or surface or broadcasting a urea in a no-till system in June on corn, you probably want some protection against ammonia volatilization if you have a moist soil out there. Enhanced efficiency fertilizers, this is the official definition. This is regulated by the American Association of Plant Food Control Officials. But it's products that allow increased plant uptake, reduce potential of nutrient losses to the environment when compared to a reference soluble material. So if you're talking UAN, these enhanced for UAN or urea, you're really looking at treated versus untreated there. So untreated granular urea compared to granular urea treated with something like Agritane or something like Lemus, probably the two big names out there. So that's what you need to look at when you're evaluating enhanced efficiency fertilizers. This is just the 4 R's. Steve showed this, and if you sat through one of his lectures, but you have your source, rate, and timing, placement. But then you also have these environmental, economic, social impacts. And one reason we want to minimize the impact on the environment is because we want to just be environmentally at least aware. Social, this is a bigger one. I think it's going to get even bigger on how people perceive agriculture moving forward. What percent of the population, does anybody know, works directly in that production ag? I think it used to be 2, they used to say 2%, but I think it's less than 2 now. So that means about 98.5% of the population in the U.S. has nothing to do with production ag or the production of their food. So which one do you think is going to win if you get into a political dilemma? That 1.5 or the 98.5? So the social issue is becoming larger and larger for us, and we need to do everything we can to kind of appease and to put their concerns, scientifically put their concerns to bed, that what we're doing is safe, environmentally sound, and it's economical moving forward. So the first category I'm going to talk about are these stabilized products. So stabilized EEFs are products that have been amended with an additive that reduces the rate of transformation. So it reduces those rates of transformation of fertilizer compounds, resulting in an extended time of availability. We have 2 classes now. We have nitrification inhibitors and urease inhibitors. As of right now, DCD, DMPP, and Nitrapyrin are the 3 nitrification inhibitors currently available. Koch Industries is getting ready to release another one. It's going to be, the active ingredient is pro-nitridine. It's going to be marketed, and I'll get in a little bit under Centuro. But as of right now, the only urease inhibitor that's currently on the market is NBPT. Now Limus, if you know Limus, which is a BASF product, it has NBPT in it as another, that's a derivative of NBPT, but in the environment it actually breaks down to NBPT. So, but NBPT is the main commercial inhibitor on the market for urease. And then we have slow or controlled release, and these are products that actually have a physical barrier on them that limit the solubility or the availability. So a polymer-coated urea, I think of it as a microscopic wiffle ball. If you think of those old wiffle golf balls with the holes all around them, that's kind of what the polymer-coated urea is. And so it restricts water flow into the granule to dissolve it, and then that dissolved urea will come out. Water insoluble, you have urea formaldehyde products. These are specialty products, so if you work in horticulture or turf industry, you'll see some of these urea formaldehyde or the slowly available water-soluble methylene urea products. But these are cost prohibitive here for production ag. So the turf or ornamental folks, y'all probably going to see a lot of that, whereas production ag, these polymer sulfur-coated urea products are what we're going to see in this category. So ammonia volatilization control. Now we're looking specifically at those urease inhibitors. Going back to this, we're going to try to impact or slow down this enzyme right here. Most commonly used, I just mentioned NBPT. I'm not promoting any products, but Agrotane Ultra is the one that's been on the market for the longest, and that use rate was 3 quarts per ton. There's other formulations now where it has a lower use rate. But it's all based, anytime you use an NBPT product, it's all based on this 0.9 by weight formulation in the U.S. And we really need to make sure, and that's per ton of urea in, not per ton of bulk fertilizer. So you're looking at urea in. So that's why for UAN we have half a rate. But when you use the use rate, that 0.09% is by per ton of nitrogen, not your application rate. Agrotane used to have their costs. It usually costs about 6 to 7 cents per pound of nitrogen to apply. The good thing about these products, they don't have to be uniform on the granule. It's not like a slower controlled release. As long as that inhibitor is on that granule in the zone of dissolution, it has the chance to inhibit that enzyme. And I talked about NPPT. It's a propyl analog, and that's used in the BASF Limus formulation, but it degrades to NBPT in soils. So this is basically what it does. So this is just say a rudimentary diagram of urease. We have this active site where the substrate, which is urea, would bind. That NBPT basically fits into that hole and doesn't let that urea be transformed by that enzyme. The technical term is competitive inhibition, and this is reversible, so over time that urea will be transformed, but the goal of this is to decrease that pH increase around that zone of dissolution so we don't have the ammonia generation that we would have if it was able to convert uninhibited. So here's this is some of my data from my PhD work. This is a Wheeling silt loam. It's taken from the Valley of Virginia. We put a nitrogen application rate of 90 pounds per acre, and we looked at NBPT rate. This is actually a different formulation. This is not Agrotane formulation. This is a different company's product. It's called Arborite Ag. But here's urea alone, and you see when we add NBPT and as we increase the rate, we see we shift these lines we get about 5 days of control before it really starts blowing off. The reaction, the inhibitor starts losing effectiveness, and that within that 5 days, and we start to see a decrease. But at the end of the 2-week trial, we still see we have 35% loss here and about probably 17 to 22% loss depending on what rate. And there's not a lot of spread. These inhibitors are pretty effective even at very low concentrations of decreasing that ammonia volatilization. Here's another study. This was done by Carmona et al. In 1990 looking at rate. They used a lot higher rate than we did in our study. They started out at 0.005, 5%. And they got really good control as well with NBPT in this study. So these are lab studies, but we're really interested in what it does in the field. And predicting response to NBPT in the field can be kind of tricky, especially if you don't get conditions conducive to a lot of ammonia loss. That's dry weather, or if we put treatments out and it rains within 24 hours, and we get a good rainfall and that nitrogen's moved below the soil surface, we're not going to get ammonia loss. But in 5 out of 10 locations from 2009 to 2012, we saw that we had ear leaf response, corn ear leaf nitrogen response over different nitrogen rates when we used NBPT. And at the other half of the locations, we saw no ear leaf response with the inhibitor. So we got a tissue or a plant response. Yield response was extremely variable. We saw 3 yield responses to the inhibitor during the study. One of those made absolutely no sense at all. The other 2 showed a positive response when we used the inhibitor. The other 7 of those 10 locations, we saw no response to NBPT at all. So I know why everybody's sitting here saying, well, why in the heck are we using these inhibitors? Yeah, they convert to transformation, but we don't really see huge yield responses over years and across environments. Well, if you hit it just right and you fall into a situation, you can get substantial yield response. So this is in 2016. We started doing some work with an experimental urease inhibitor as well as Agrotane Advance. This is at the Tidewater AREC. This is 100 pounds of N per acre applied with Agrotane Advance as urea. This was taken in late July. You see right here we have dark green leaves all the way to the bottom of that plant. When we looked at untreated urea, we went out and took some photos. 180 pounds of nitrogen. You see the plant's severely nitrogen deficient. This is in late July, firing up the plant, the senescing leaves. So what did that translate to? This is a little bit after, about 3 weeks after we pulled the corn ear leaf at green silking. But this is our grain yield response at this site at the Tidewater AREC. We had an 88 bushel yield increase from untreated urea at 240 pounds of nitrogen. And we've yielded about right at 280 bushels to the acre when we had the experimental urease inhibitor, about 270 with the Agrotane Advance. With urea alone, we were at 192. So the weather hit us just right. We applied the fertilizer. It was a moist, wet soil. 5 days after application, we got about 1.5 inches, 2 inch of rain that moved the fertilizer in. And what had happened, if you remember our lab studies, we got about 5 days of control. So we did not lose hardly any nitrogen from our EEF with the urease inhibitor during that 5 days, where we lost a large amount of nitrogen from our untreated urea. And this is not typical of what we see, but this will pay for using an inhibitor multiple years if you run into this environmental situation. This year, I don't have the data up here in this presentation, but this year we also saw about a 50 bushel increase in yield again in our field trials this year. So we actually were able to repeat this. But when environmental conditions are right and we have high corn yields, you can see a substantial response in yield. So responses to NBPT, one of the biggest things is that environmental conditions play a huge role. We've gotten sparse responses in the past, but NBPT does do what they claim that it does in terms of affecting that transformation from urea to ammonium. It controls that. We can't always predict what the weather is going to do, but what I recommend to growers, if you're in a granular system, a granular urea system, broadcasting over corn, I would recommend that you use a urease inhibitor in that system, especially if you're putting it out when you have warm temperatures and moist soil conditions. Oh, this is another important point. This bottom point, efficacy of NBPT in acid soils decline as soil pH decreases. So NBPT is not a very stable molecule once you get below a pH of 6. So it degrades. And what we see in our lab studies, if we have a pH about 5.5, we get about that 5 days of control turns into about a day and a half. So soil pH plays an important role. And actually, this experimental urease inhibitor is something that they focused on, a product they focused on really improving that control in low pH soils, which we have in the Mid-Atlantic and in the Southeast coastal plain fairly frequently. Other urease inhibitors on the market, these are just some that have been, I'm not going to talk a lot about them. Basically, NBPT and NBPT and BA-Lemus formulation is the only other commercialized urease inhibitor that you're going to find that does what it says that it will do in the literature. So moving on to nitrification inhibitors. So this is an area that's becoming, we have some new things coming online. Nitrification inhibitor, this is again the nitrification reactor. But what we're really going to focus on is this nitrous ammonium. This is where we're going to inhibit this process because we don't want to inhibit it here. If we stop this bacteria but let this one continue, we're going to have buildup of nitrite, and that's going to be detrimental to our plants. So we want to stop this reaction on nitrous ammonium, and that's what these products really focus on doing. So here is a table. Up here, this is the chemical formulation. This is Nitrapyrin N-Serve Instinct 2, which is used for UAN and urea. And then this other one, DCD. These are the two big ones. I've heard BASF is going to start bringing DMPP to the market again. I don't know when that's going to be available, but DCD and Nitrapyrin are the two big nitrification inhibitors that are currently on the market. And for us in this area, Nitrapyrin is going to be under the trade name Instinct 2. So this is Dicyandiamide. This is DCD. It's actually a slow release N compound itself. It's about 65% nitrogen. It's bacterial static effect. That means that it slows down the bacteria's metabolism. It does not kill the bacteria. It just slows them down. It impedes their transformation. Depending on the conditions, you can get 4 to 6 weeks control of nitrification. Can be used with forms of ammonia containing fertilizers, and it's usually mixed at a rate of 5 to 10% by weight of fertilizer blend. Some of the products are trade names: Super U, U-Flex, U-Max. DCD right now is exclusive rights is with Koch Agronomic Services, so these are all Koch Agronomic Services. Super U is actually the ag formulation. It has NBPT and DCD in the mix. U-Flex and U-Max are turf products. Nitrapyrin was developed by Dow. Again, trade names are N-Serve Instinct 2. This N-Serve is used with Anhydrous, and they get very good results with it, up to 30 weeks of nitrification control in cool soils, and it's usually applied in fall with the Anhydrous. Instinct 2 is for use with UAN and urea. This is bactericidal, so it has the EPA label. It does kill the bacteria in soil systems. And here's just some, I think this is from the Midwest. This is Nitrapyrin. This is a corn trial. Again, you see nitrogen deficiency resulting from leaching probably here. And then where N-Serve was used with Anhydrous, you see no nitrogen deficiency. And then they also saw quite a bit of a yield bump. These are tons per hectare. But I mean, you're averaging about 2 to 3 tons per hectare grain increase with the use of Nitrapyrin in this study. DMPP, I mentioned BASF, I think is trying to bring this to market again. The trade name would be Intech. Its absorption in organic soil surfaces may play a key role in the efficiency of it. But again, it does stop nitrification or inhibit nitrification from occurring, which reduces your leaching losses, but also reduces the production of NOx gases, greenhouse gases, that can be evolved by not allowing nitrate to build up, then be denitrified into NOx gases. Other nitrification inhibitors coming online. There's a new one from Koch Agronomic Services called Centuro. It's pro-nitrodene. They just got their label approved by EPA, and that's probably going to hit the market maybe next year. but that's a new formulation, a new chemistry for nitrification inhibition. Is anybody familiar with ammonium thiosulfate? That's a 120026S. It has been documented that it will also is an inhibitor of nitrification itself. I think it has a lot to do with the thiosulfate part of that, that fertilizer. And then here's some other ones, just some chemical names of some other ones that have been tested. Neem or Niemann coated urea has been documented to be a nitrification inhibitor. So the nitrification inhibitors, overall what they do is they lower the NO2 or NOx gas greenhouses, they limit nitrate leaching, maintain the N in ammonium form, which is critical because ammonium is not as prone to leaching as nitrate. It can be held on the cation exchange capacity. But again, just like ammonia volatilization and the NBPT, yield results can vary based on environmental conditions. But these products that I listed do inhibit nitrification in soil systems. So one thing we really looked at, and you have a lot of products, Super U is one of them, where you have NBPT as well as a nitrification inhibitor. And my lab really looked at, well, what happens if you put both on urea and you broadcast it out there? And what we wanted to see is, because with nitrification inhibitors, you're stopping that reaction at ammonium. Well, for something like ammonia loss, if you stop the reaction or slow down the reaction so you have a buildup of ammonium, you potentially have the potential for more increased ammonia losses in our agroecosystem. So we looked at this in the lab, and what we found is when we put DCD or Nitrapyrin, it doesn't matter, on granule urea, and then we coat it with NBPT or just coat it alone with the nitrification inhibitor, we actually increase ammonia losses from that fertilizer. So if you're broadcasting or surface applying UAN or urea and you're using a nitrification inhibitor to prevent against leaching, you better have the urease inhibitor NBPT product in there with it. And because here is DCD alone, we went from about 35 to a little over 40% loss. But I don't have the agrotane only, but what's really scary is we're typically seeing about 5 days control. We bumped that to 3 or 4 days control. We shortened that window of efficacy for that NBPT just by adding a nitrification inhibitor in the formulation with it. And these are 2 different NBPT rates and 2 different DCD rates. Same thing with Nitrapyrin. This is the same thing. And actually, Nitrapyrin seemed to be a little worse on the same soil types. And as we see that these losses actually, when you had DCD, even with NBPT, were significantly the same at the end of a 2-week trial as untreated urea. It delayed it initially, but the overall cumulative loss in these trials was the same as untreated urea, which was striking to us looking at Nitrapyrin on granule urea surface applied. And then here's Nitrapyrin with no NBPT on the granule. You see we increased it about 10% over what untreated urea is. So this is very telling, and what our recommendations are now. If you're going to surface apply urea, UAN, and you're going to put something like Instinct 2, which is Nitrapyrin, in your blend, then you probably want to go ahead and treat it with an NBPT containing urease inhibitor. So slow control release nitrogen. Just going to run through this real quick. So here's some incubation trial where we looked at urea, untreated urea, ESN, which is a polymer-coated urea, which a lot of y'all in this room are familiar with, and then Super U, which is the dual inhibitor with nitrification inhibitor as well as a urease inhibitor. And so these are hours after N application. We go all the way out to 3 weeks. 504 is 3 weeks, 336 is 2 weeks. The yellow bar here is untreated urea, and you see ammonium builds fairly rapidly. Within 24 hours, we have about the maximum amount of ammonium that we'll have. Super U is a little delayed. It's probably 48, 96 hours. We're equal to urea. And then ESN is releasing slower. At the end of 3 weeks, this equals about 60% of the ESN, the nitrogen in ESN was released within 3 weeks. Now, I don't know, I'm not real familiar with their release curves, but from people I have talked to, this is a lot faster than what some of their literature says. And like I said, I haven't brushed up on my ESN, but we get about 60% release at 25 degrees centigrade, which is about 72 degrees Fahrenheit, in soil incubations with ESN. This is a study that we were looking at. We have 3 experimental resin-coated or polymer-coated ureas that we looked at, compared them to ESN and then our grower standard in corn this year. And we have a check. So the black bar is our check. This is corn ear leaf nitrogen. So with 0 pounds of nitrogen, we're at 1.5% corn ear leaf. Our grower standard, which is 30 pounds of nitrogen at planting, followed by 130 pounds of nitrogen at V5. We were up around 2.8% in the ear leaf. And at 3 different nitrogen rates, 80, 160, and 240, we see that we increased as nitrogen rate went up. But what was very striking is that these polymer coated, these last 4 right here, 100% of the N went out at planting of the corn. So that we didn't put any more nitrogen down in season, and it looked like 2% at the 80 pounds, which would not be a rate that a grower put out. That's a sub economic rate for us. 160 pounds is where we would typically be on our soils. Our guys typically shoot for 150, 200 bushel corn. So that's where we would typically be a nitrogen rate. It's very comparable to our grower standard, our split application. And then at 240 pounds of nitrogen, you see that we actually increased that. But our grower standard was basically at the same level as the control release with the higher nitrogen rates. But we look at yields, and this is what pays the bills, and this was very striking to me. I wasn't expecting the polymer-coated or slow-release materials put out all at planting to perform similarly to our current practices in terms of efficiency. Our check plot with no nitrogen did about 80 bushels to the acre. Our materials that we put out, the slower controlled release, at 80 pounds, so we just increased the N rate by 80 pounds. We went from 80 bushels to 140 to 150 bushels. And that was 80 pounds of nitrogen at planting with the slow controlled release. When we went up to the 160 pound rate, we were around that 200 bushel per acre yield threshold, which was, I had no aspirations of hitting that by putting all the nitrogen out up front. But it looks like these materials performed very similar and released on a time frame that the corn was able to utilize it and really make grain yield this year, which we had a pretty good corn yield. When we went up to the high nitrogen rate, we were up around 250 bushel corn. So they still performed even at the higher rate. So that means that these materials released in a way that made it available for the plant, and the plant was able to utilize that nitrogen. So it looks like there's some very good technology on the market and currently being utilized across our growing season for ESN. But this is just one site, 1 year, so I stress we really need to repeat this system over multiple sites, multiple years before we use it. But anyway, just want to put a summary up for y'all. Soil type, texture, CEC, other physical chemical properties really impact loss patterns, loss mechanisms. And could impact enhanced efficiency fertilizer performance. EEFs that contain the stabilizers, NBPT, DCD, Nitrapyrin, DMPP, do stabilize nitrogen in certain forms and limit transformations. But predicting whether we're going to see an impact in yield from these products is kind of tricky, and environmental conditions need to line up. And then also know your placement system and your nitrogen management system, and use the enhanced efficiency fertilizers that best meet your system. So like injecting UAN, you probably don't need a urease inhibitor, especially if you're putting it down 3 to 4 inches in the soil. But surface applied urea in a no-till system, you're probably going to need a urease inhibitor out there to limit your losses. So with that, I'll take any questions.
Thank you.
Mm-hmm.
We have time for questions. No questions. Where are we at?
Yeah.
Well, I was going to ask, I could probably back into it, but do you have the NUE from those slow release inhibitors for yield? Like, in other words, was there still any left over?
So yeah, I mean, we have crop yield, but we didn't measure uptake in that study. So actual nitrogen uptake and biomass to see what the plant actually took up, but we could do like a grain NUE, like bushels per pound of nitrogen, but it's fairly consistent in that study with a 1-to-1, which is typically what we would see, 1 bushel. Maybe we're a little less than some of our systems, you know. I think we're around 0.75 pounds of nitrogen per bushel of grain now. So.
Thank you.
Yep.